Please on your videos, or I told already what will happen. You will be out of the meeting in few minutes. Okay. So if you are joining online, please make sure a video is on. I am not going to say it 100 times on the video. Beginning I am saying. After that, if you are out of the group, don't say anything to me. It will be your responsibility. Okay. So Amruta, Jay Aditya, Kapil Vel, Mahesh Raj, Navadeepika, Nitya, Salvin, Mario, Srinidhi, Tanishka, Uttara and Vignesh. I hope you are able to hear me, and yes, as I said, your video must be on. If your video is not on, then you will not be there in the group. Srinidhi, I am saying this to you, then don't say to me, sir, why you removed him from the group. Fine. So Srinidhi, Jayaditya and all, everybody's video should be on, and you have to be as interactive as you can be in the regular class. Fine. Even for you, those who are sitting in the offline section, and those who are going to join online. If tomorrow you are also going to come online, you have to make sure that the same amount of discipline you have towards the class. The motto of us is to learn something, isn't it? So don't spoil that motto. Don't come and do something nonsense there or here. I know some children are coming here for their friends, some children are coming for some reasons. Everything is known to me. But now the board has come, almost 2.5 months away from today. So become serious and don't waste your time by doing anything else. Please be very attentive in the class, and if you have any doubts, you need any clarifications, ask me immediately. Okay. This chapter I started in the last class itself, but I will assume it is 0, and once again I will start from the beginning, almost. Okay. So once again I am repeating, you have all the rights to stop me whenever you want. It's not like I have to, like you have to meet me after the class. It is a 2-hour class, it's a long class. Today we will try to finish Nuclei chapter, how much maximum we can finish, and for that I want it to be highly interactive with me. Guys, those who are joining online also, same thing applies to you. Please be interactive, ask me questions. You are free to ask me questions. Stop me whenever you want me to stop. Okay, your audibility is excellent. I'll be able to hear you. Fine, Amruta, clear? Just say yes. Jayaditya, is it clear? Okay, Kapil Vel, is it clear?
Yes, sir.
Okay, I think audibility is fine. I am able to hear you loudly. Fine. So in the last class, we started talking about a new chapter, which is nuclei. Maybe the first section of this chapter you would have felt some difficulty in understanding, but let us try to make sure today that this chapter is not that difficult to you after this class gets over. So by the end of today's class, our aim is to become comfortable in nuclei, and believe me, nuclei, atoms, dual nature of matter and radiation, semiconductors, wave optics even are scoring chapters. I am repeating this, they are scoring chapters. Small chapter giving you mark. What else you want? It's 1-day chapter only, and that small chapter can give you 5 marks. Certain questions are there. I am going to tell you what questions will come. Those questions, if you are thorough, marks is confirmed. Theoretical questions will come from here. You should not write some unwanted stories. Theoretical questions also should write proper things what is required for a question. So please make sure that you are like clear in this chapter. And once again I am repeating, out of all the physics portion, I always believe that the easiest part of physics is modern physics. Modern physics starts from dual nature of matter and radiation. So all these chapters are really easy. If you are still not feeling it is easy, then you need some more practice, you need some more learning. Once you learn all the chapters, definitely you will feel this is easy. Okay. Coming back to the class. So in the previous class I taught basic things, not binding energy level of concept, but at least you remember what is the meaning of nuclei, what is there inside the nuclei, isn't it? And how is nuclear force helping the stability of the nucleus. All these things I taught in that time, and based upon that, let me ask a few questions to you. I hope you remember those things. Like first question, and the most basic question is, a nucleus consists of dash and dash together called as nucleons. My God. Neutrons and electrons, sir. Protons. Neutrons and protons. Obviously, this kind of question comes, then give yourself a party. Right. Next is atomic nuclei having same atomic number and different mass called? So, then what is isobars? Same mass number and different atomic number. Then what are isotones? Same number of neutrons. It means if you subtract A with Z, A is mass number, Z is atomic number. If you do A minus Z, that is number of neutrons. If two elements have same number of neutrons, then they are called as isotones. Always remember that isotopes are of same element, whereas isobars and isotones are always of different element. Keep this in your mind. Hydrogen has 3 isotopes, isn't it? Protium, deuterium, tritium. Chlorine has 2 isotopes. Chlorine 35, chlorine 37. Like that, same elements can have different isotopes. Isotopes means in which different, different ways an element can exist. It's not like in the whole universe the hydrogen is only 1 H1. In the universe we have 1 H1, we have 1 H2, we have 1 H3. All 3 are there in the universe. So, these isotopes means what are the possibilities of an element to exist in the nature. So, if it has 3 possibilities, it has 3 isotopes. If it has 2 possibilities, it has 2 isotopes. Like that, almost all the elements have isotopes. You may not know by now, but it's true that almost all the elements in the periodic table has some isotopes, and who knows, tomorrow we may find more isotopes also. Known to human being are these, and periodic table is unimaginable. We have 1118 elements now. Who knows, after 10 years or after 100 years, we may have 1180 elements also. Suddenly we get a new asteroid from somewhere, and in that asteroid we will have many elements, new elements. Possible, right? Known universe, whatever we have seen till now, in that we have able to find and size how much elements? 118 elements, right? So, nucleus is the part of the atom which contains most of its mass and all the positive charge, isn't it? I told when I was teaching about gold foil experiment, I have told this, that nucleus is that part of the atom which contains all the mass and almost all the positive charge. So, if you weigh an atom, its weight is all because of its nucleus. That is why we say nucleus is the central massive core of an atom where all the positive charge exist. And I also told in the class to you that the proportion of nucleus inside the atom is like a dot drawn in the room. How much a dot is occupying a space, that much space is only occupied by a nucleus inside the atom. Very, very, very concentrated it is, very concentrated. Almost the most concentrated thing in the universe will be atom, nucleus only. That much concentration is there. Too much less space is there where you have almost all the mass. I hope you are understanding this. So, that is a nuclei. Then, if you see, let us see another question is there or not. Yes, one more question is there. What is this? Atomic nuclei having same mass number but different atomic number are called as what? They are called as isobars, obviously. Next is isotones also is there. So, we are going to start about the topic today. As I said, today what we are going to learn, first I will talk about the size of nucleus, then I will talk about the binding energy. I know some of you have doubt in binding energy. I will try to make it clear today. And after binding energy, we will learn about the nuclear forces, and then if time permits, we will also talk about nuclear fission and nuclear fusion, which is the most interesting part of this chapter, and it is a very simple thing. If you are binding, fission, fusion are nothing, it is just child's play for you, if you are very clear in binding energy concept. Okay. So, what is the topic I have, like you can give the heading in a notebook also as size of the nucleus. All of you please take the notes parallelly. It is not like I am going to teach and you are going to listen, you are going to take the notes as you are taking in the regular class. So, radius of the atom, or I should say nucleus, we have already kind of understood while doing the gold foil experiment, isn't it? So, I said you when we do gold foil experiment, then we bombard the nucleus, gold nucleus or gold atom with alpha particle. Alpha particles are positively charged particle, and it goes towards the gold atom, and at distance of closed approach it reverses back, isn't it? I mean, out of all the particles that are going, 1 in 1 million, I told you, 1 in 1 million particles are reversing their path. and that particle, why it is reversing its path? Because it is going very close to nucleus, and then nucleus is highly positive, the positive repulsion happens, and it is able to reach the maximum distance, that is minimum distance from the nucleus, and it takes a turn. How to find distance? We can equate kinetic energy to potential energy. Kinetic energy of the alpha particle, whatever you take, it will, like if you are using bismuth, it will be 5.5 MeV. If you are using some other radioactive element, it can be 6 MeV, 7 MeV based upon that. So that is in your control. What is the alpha particle's velocity? So what is the kinetic energy of alpha particle? That must be equal to its potential energy, and potential energy formula is K Q1 Q2 by R. I hope you remember all these things. So this thing we have done, I think, even SSM Nagar I have taught in the last class, isn't it? So if you remember, if you have this gold nucleus, and I remember when I am bombarding with alpha particle, some particles are going straight, some are having minimum deviation, some are having some deviation like this, and only 1 in 1 million particles are getting deviated at direction. This distance is called as small d, which is called as distance of closest approach. And how to find this value? I told you at this point equate the kinetic energy and the potential energy. So kinetic energy of the alpha particle must be equal to K Q1 Q2 by R. What is K Q1 Q2 by R? Potential energy formula. When you put the equation, kinetic energy will become equal to K. And what is Q1? Q1 is the charge of alpha particle. How much is the charge of alpha particle? 2 plus, so 2e it will be, good. And what is the charge of gold? 79e. If it is some other nucleus also, I will take it as Ze. Z is the atomic number of the element that we are using. If you are using gold, it will be 79 divided by R. So what will be the kinetic energy formula? Kinetic, actually I can write D here because I am taking it as distance of closest approach. Kinetic energy will become equal to 2 K Z E square by D. So what will be D from here? D will become equal to 2 K Z E square divided by kinetic energy. By this formula, for a particular kinetic energy, we can find what is the distance of closest approach. Now, how it helps you? It helps you to understand that nucleus must be smaller than that. If your alpha particle is able to reach this distance, and this distance is before the nucleus, it means nucleus size will be smaller than that. If we put the value of kinetic energy as 5. Bismuth substance for radioactivity. So in that case, you get the D value around 30 Fermis. If you are using 7.7 MeVs, then you are getting around 43 Fermis. So that depends. But one thing is sure, we are going to get the value of D in range of some Fermis only. 15, 20, 30, 40 Fermis. Fermi is what? 10 to the power minus 15 meters. Fem2 also we call. So Fem2 or Fermi is 10 to the power minus 15 meters. So you can understand that this value small d, how nucleus is, right? Generally, the radius of the nucleus formula R is equal to R naught into A power 1 by 3. That is, R naught is a constant, I will talk about that now, and A is the mass number. A is the mass number. This is the formula which is used to find what? It is used to find the radius of the nucleus. What is the formula? R is equal to R naught into A power 1 by 3, root of A. So now if I just come back to the slide, the same thing I have told here also, where if you see the first thing what I have told is size of nucleus. How much it is? Approximately 10 to the power. How I said this, are you getting? Because of alpha particle, that is experiment. In foil experiment, I have already got the answers to somewhere near Fermis. So I am saying the size of nucleus is approximately around 10 to the power minus 15 Fermi. It can be plus or minus, but near that Fermi's value only it is there. So I said you that it is estimated by the alpha particle experiment, and the formula also just now I derived the same thing. Kinetic energy is 1 by 4 pi Z square by D, and from here D you can get 2 Z square by, this thing will come down. I just told before that. And radius of the nucleus is given by R naught A power 1 by 3, and what is the value of R naught? 1.14 10 to the power minus 15 meter. So you can see from here that radius of the nucleus is coming around 1.1 Fermis. Are you understanding? If you put the value of R naught as 1.14, that is this value, R naught value is 1.1 Fermis. If R naught is 1.1 Fermi, you can put the corresponding value of A and find what is the radius of the particular nucleus, isn't it? So different nucleus may have different radius. Is it clear to you? Very basic thing I am talking. Can I go to the next thing? Okay, I am waiting for a minute. If you want to write something, please make a note of it. If you want to write something, please make a note of it. Is the AC reaching there? Mildly, it will come in some time. Can I go to the next page? I will share the PPT if you want. I mean, write main things. I am not saying not to write, but don't spend too much time on writing very basic things. I am going to the next page, guys. If you are missing something, I will share the video or PPT, whatever. So, yeah, this is one of the most important point I am going to talk, because from here the questions are coming in the board examination. If you see, I have that volume of the nucleus is directly proportional to the mass number. Why I say like that? Because volume is equal to, volume of sphere is how much? 4 by 3 pi r cube, and what is r cube? Radius, and r is related to what? Atomic number, that is mass number. So I can say that volume of the nucleus is also depending upon the mass number. Now I will talk a little more about that. I think, yes, density of nuclei. So what is density formula? Density is mass by volume. So what is volume? 4 by 3 pi r cube, isn't it? Volume is 4 by 3 pi r cube for a sphere, and r is what? R naught into a power 1 by 3. If you put cube of that, it will become r naught cube into a. What is being done, you are understanding or not? 4 by 3 pi r cube I have put the value of r as r naught into a power, and then mass, you know, mass number is a, and if you want to find the mass number in terms of kg, multiply by 1 AMU is equal to 1.6 10 power, obviously. So you get the value in this thing, and for density what you will do? Mass by volume. This mass divided by the volume, if you do, you will see that what will happen, A will get cancelled. I will just write one more thing, yes. Now I am going to speak about this. If you see this formula, A will get cancelled, right? What is the meaning? Meaning is density of nucleus, don't you think it is independent of mass number? This question has come in the board examination in MCQ category. Volume of the nucleus is depending upon the mass number, but of the nucleus is independent of the mass number. It means if you have more particles in the nucleus, obviously its size will be bigger, isn't it? So what is constant? Density is constant. I hope you are getting my point. And if you have less number of nucleons, then the size will also be smaller. It's going to remain same. Density is going to remain same. Density of the nucleus is depending only on the what? If you see from here, it depends only on what? R naught, which is a constant value, not radius. R naught alone, which is a constant value. It does not depend upon the mass number. So whatever nucleus it may be, what will be its density? 2.67 10 to the power 17 kg per meter cube. It's a quantity. Are you getting my point? Whether it is hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, whatever element it may be, its density will always be same. And how much it will be? It will be 2.67 10 to the power 17 kilogram per meter. I said that for which you are saying, proportional or inversely proportional. What you are asking? Yeah, write that if you want to write. Write that volume of a nucleus is directly proportional to its mass number. Volume of the nucleus is directly proportional to its mass number. Volume of the nucleus is directly proportional to its mass number, whereas density of the nucleus does not depend on its mass number and is a constant. Does not depend upon mass number and is a constant. And you can write the value also. Its value is 0.67 10 to the power 17 kilograms per meter cube. Is it clear? Very basic thing. So from here MCQs are coming, not numericals. From this topic what is coming? MCQs are coming, and sometimes a 2-mark question also is coming. How the question is coming, I'll tell you that also to you. See, we know that R is equal to R naught into A power 3. So from here I can write R is proportional to A power 1 by 3. Can I write like this? Then can I write R1 by R2 is equal to A1 by A2 power 1 by 3? Check the board exam paper. Last 5-year paper itself you check. 3-4 times question has come from here. That is, if mass number becomes double, what happens to radius? If mass number becomes 4 times, what happens to radius? By this you can find. If A2 becomes 4 times of A1, then how much it will become? A1 gets cancelled and it will become 1 by 4 power 1 by 3. Solve it, get the answer. 1 by 3 means cube root. Are you getting my point? They may ask you the question, mass number is becoming this much times. Yes. How will you solve this kind of question? This formula, R1 by R2 is equal to A1 by A2 power 1 by 3. This is 1 by 3, okay, cube root of that. So from here questions are coming. And second question comes like density of nucleus. You have to write it is independent of its mass number. Can I go to the next page? I hope it is clear. Very basic. Okay. So same thing, density of nucleus is independent of the mass number. So density of nuclei is same for the atom of lithium or atom of gold. Its mass number will be different, its volume will be different, its size will be different, but its what will be same? Density will be same. Okay, I hope you understand. So this you should understand. If you see a nucleus, no, you know how it will be? Its density will be maximum in the center, and as you go away from the nucleus, its density will start reducing, and it will be almost zero. So nucleus, if nucleus is like this, then its density will be maximum where? In the center of the nucleus, and as you are going away from the nucleus, no, its density is reducing, almost becoming zero if you are on the outer surface of the nucleus. Question comes from here, you know how? Graph question comes from here. They will draw 4 graphs, they will say which graph depicts the density of the nucleus correctly. Like this, where as you go away and is radius 0. I would have drawn here also. If you see the PPT, you will see the perfect graph. Yes, this is the graph. This question comes from the board examination. They will ask like which graph represents the relation between density and radius correctly. This is the graph where as the distance from center increased, the density of the nucleus is reduced, and where is the density maximum? At the center. So what is O? Of the nucleus, where the density is maximum. Where you have reached this point, and this, if you have reached the surface of the nucleus, then its density becomes 0. Is it clear to you? I hope it is clear to you. Very simple, this kind of questions are coming. Very simple theory questions will be coming from here. Like these questions can come. Graph based questions can come. Can I go to the next slide? Up to here things are fine. Simple topics only now. I hope who are attending online, I hope you are writing whatever I am telling. Anushka, Uttara, writing? Confirm by saying yes. Navadeepika, you are able to hear me?
Yes, sir.
Are you able to understand whatever I am telling? If any problem is there, stop me then and there itself, okay? So, I will go to the next slide, and this slide is very important for today's class, where I am once again starting to talk about binding energy. Fine. So, this topic I started in the last class also. I don't know how much you understood, but today, believe me, you will understand and go. Okay, fine. I said you that in nature, it is found that nucleons, when I say nucleons word, what does it mean? It means protons and neutrons. If I find the total mass of the nucleons independently, and if I measure the mass of a nucleus by some experimental experiment like spectrography or something, you will find that the mass, the observed mass, the experimented mass is always smaller than the individual mass. It means what I want you to see here, carbon has how many protons and how many neutrons? 6, isn't it? Hydrogen, helium, lithium, beryllium, boron, carbon. 6th element of the periodic table. It will have 6 protons and 6 neutrons. So, when I measure the mass of 6 proton and 6 neutron, and if I measure the mass of carbon, same 612 only, then I will see that when they are independently, their mass is higher than their mass when they exist in combined state. Are you understanding? If I assume the mass to be in AMUs, then here how much AMUs it will come? 12 AMU, isn't it? This is 12 AMU, and this is what is this issue 12 AMU, and when you observe, no, it will come as 11 point something AMU. I will repeat this. If you have a particular element in the independent state, for example, oxygen, how many protons, how many neutrons? 8 protons, 8 neutrons, and 8 electrons also in the atom. Nucleus will have 8 protons and 8 neutrons. If I multiply the mass of each neutron with 8, if I multiply the mass of each proton with 8, what do I get? I get expected mass of the nucleus, isn't it? 8 into mass of proton, 8 into mass of each neutron will give me total mass of the nucleus. Am I right? And then when I observed the mass of oxygen atom by experiment, it was found to be lesser than that, not 16, 15 point something. It means what? Some mass is not there. That mass which is lost, or that mass that is not there, is only called as mass defect. What is mass defect? Mass defect is the difference between the mass of the nucleons when they exist in combined state to when they exist in independent state. And I told in the last class to you that whatever mass we have, that mass is actually energy. Einstein said that every mass is energy. You have a mass, you have energy. I am a mass, I have energy. Anything that has mass will have energy also. How much energy? Delta m into c square, that is mc square. So, whatever mass defect is there, mass defect is, yes, it is the nucleus of the nucleons. I will give an example to you now to make it little more clear. If I give one example, see this example from NCERT book only I have taken. One second. Yes, this is actually from NCERT book I have copied and pasted here. So, if you see, you will realize that I am talking about which atom? Oxygen atom. This is oxygen atom, exists in O2 format, whatever. This oxygen atom, one oxygen atom is having 8 neutrons, 8 protons and 8 electrons, am I right? Anyhow, this is not required because we are going to find only nucleus mass. So, nucleus mass will be 8 into 1.00866 plus 8 into 1.00727, am I right? If you add these two, you are going to get 16.12744 U. What is that? It is the expected mass of the oxygen nucleus, am I right? Please understand what I am trying to say. this value is mass of each neutron, this value is mass of each proton. If the oxygen has 8 neutrons and 8 protons, then the mass of the nucleus expected will be this much. Read the statement. The atomic mass of oxygen found from the mass spectroscopy experiments is seen to be how much? 15.99493 U. Expected was 16.12744 U. If I subtract both, you are going to get some value 0.13691 U. What is this? Mass defect. And if I want to find how much energy it creates, what you will do? You will multiply delta m with c square. So generally, if you want to find the energy in terms of electron MeV, what we do, we multiply this value with 931.5. I told you in the last class. If you multiply the mass defect with 931.5, you get the answer directly in MeV. Or else, no sir, what is this? I don't understand. Then what you do? Take delta m, whatever value you got, multiply it with what? C square. You will get the energy in joules. Divide by 1.6 10 minus 19, convert into electron volt. Same answer will come. So for that, directly we have found and kept it for you, ready to serve. 931.5 is the value. If you multiply this 931.5 with the mass defect or the mass, then you get energy in MeV. Are you getting my point? So how much energy it creates, you can find easily with the help of this 931.5. Are you getting? This is the binding energy that exists inside the nucleus. If there is any nucleus, how much binding energy it has is all because of what? Because of its mass defect. Am I clear in whatever I have said? That's why if I go to the previous slide, you will realize that the same thing I told in the previous class also, that binding energy is what? Z is number of protons. So number of protons into mass of each proton, plus A minus it will be number of neutrons. Number of neutrons into mass of each neutron. This whole thing is going to give you the expected mass. This is what? This is expected mass. And what is this M of nucleus? Observed mass, experimented mass. Subtract both, what you will get? Mass defect. Multiply mass defect with 931.5, you will get the energy in MeV. If you multiply by C square, you will get the energy in joule, your wish. If you get in joule, your headache to convert into MeV. How? By dividing with 1.6 10 to the power minus 19. If you want to do, I don't have any problem. Are you getting my point? This will give the binding energy of the whole nucleus. If you divide by total number of nucleons, you will get for each nucleon how much binding energy it has. Those who have gone to some other place for some time, listen once again. Binding energy, the whole nucleus can be found by this expression, right? That is gold nucleus, this is binding energy. But if I want to find binding energy per nucleon, then I have to divide the binding energy by mass number. If 17 or if 50 nucleons are having 100 energy, 50 is having 100 energy, how much one is having? 2. How you found 2? 100 by 50, isn't it? Same way, if 16 nucleons is having this much energy, then how much one will have? That energy divided by 16. So when you divide the binding energy of a nucleus with mass number, what do you get? Binding energy per nucleon. It is called as BEN, the most important thing of this chapter. The whole chapter, fission, fusion, everything is based upon this only. How fission takes place, how fusion takes place, how the energy is released during the fission fusion. Every logic is based upon BEN only. What is BEN called as? Binding energy per nucleon, which is binding energy of the nucleus per unit mass number. I remember when I was teaching you the previous chapters, I told you in modern physics, calculations will be very, what do you say, not difficult, I will say lengthy. Time has come for that, isn't it? So let us take one question. All of you are having notebook here? Yes. Online people, don't use calculator, do by your hand, okay? Don't use any internet calculator or anything. And start solving the first question. The first question on the screen is calculate binding energy per nucleon of calcium. They have, for your easiness, they have given you the observed mass of the calcium, which is 39.962589 U. Remember, don't round off. Don't take it as 39.9 means 40. You will not get the answer itself, because the answer will itself come in decimal only. So 39.962589 U is the observed mass of the calcium. They have also given you mass of each proton is 1.007825, and they have given the mass of each neutron is 1.008365 U. And this I have told you already. 931 they have told, not 10.5. That depends. So now you have to find binding energy per nucleon of what? BN of calcium. I will give you 5 minutes. Too much time, but I will give you 5 minutes, because I know you are weak in calculation. Get me the answer. 5 minutes in your hand. Timer, please. Don't put this timer. Put that Zoom timer. Guys, you have to solve. The timer is going for the online kids. Timer is in apps. You have to go to apps. Yes, click there. Yeah. Online children, again I am repeating, don't try to use calculator in exam. There is going to be no calculator. Take your time and do by your hand. It may take time, no problem, but do manual calculations. Same formula, Z into MP plus A minus Z into Mn, subtract with observed mass, get the binding energy by multiplying by 931, divide by number of nucleons, that is 40, and you will be able to get the binding energy per nucleon of calcium. This kind of numericals are coming in the examination. Please, please, fast, fast, fast. Two and a half minutes left. Yes. Binding energy per nucleon is that value? Divide by 40 you did. BN, that is maximum possible, is 8.6 only, that is for ferrous. If you do, you will get wrong answer. I mean, okay, at least 4 digit after decimal. At least 4 digit of decimal you keep. 5 you keep, it is good. You kept 3 only. Okay, what is the answer you are getting? Tell. What is the binding energy you got, Briti? How much?
354.
That itself is wrong. Wrong means maybe because of approximation it became that much wrong. Anybody else? Any binding energy at least? Leave B in. B, at least B anybody got? BE, binding energy. Oh, still you are not, then ZMP,
For me, B is coming around
8 point? 8.8 is not possible. 8.85 not possible. Yeah, what is the maximum being possible? Iron 8.65 only, I think 8.7 around. That is the maximum possible value. Approximation made mistake, no? Last 30 seconds, huh? 3 point something, very low. No, that much low be in. That much approximation, very wrong. Anybody else binding energy? Online people? Any value of binding energy that you have got? Tell Sanjay. Binding energy. Binding energy per nucleon 44. Then 344. How much? Very far from the answer. 130. Time is up, time is up, time is up, time is up, time is up. Any answer? Praneep Dharan, Jay Aditya, Vignesh, Magesh Raj, Salvin, Tanishka. Any answer? Binding energy per nucleon cannot cross 8.6. That is too low. It will be very high. Yes, guys. Any answer? Nobody? Again, 8.9 is not possible. How much binding energy you are getting? Can you tell me that at least?
About like 342.6.
340?
342.6 MB.
342 if you are getting, 342 by divided by 40 if you do, how much you are getting? See the answers I will tell you. Ans 345. 45. Mistake is there. So I will do step by step. See, I have answer in my hand, so I will write on the board. I can multiply also, but why I should struggle for you? I mean multiplication only, that is not testing my knowledge. Okay. So ZMP plus A minus Z into Mn, you found this value, how much it came? Z is how much? Z 20 into what is MP given? 1.007825 plus what is A minus Z? 20 into what is Mn given? 1.008665. Multiply how much, multiply and add how much you are getting, you know? It should come approximately 40.3298 approximately. Did you get this? 42. Here itself you made mistake then. Did you get this much? Very good. When you multiply this value, this is 40 not 46, okay? Subtract. Sorry. You have to subtract this value with what?
39.9625.
Subtracted by mass of the nucleus. That is given as 39.962589. Delta M is coming 0.367211. Did you get this? What? How much you got? How 0.00? You're doing mistake in calculation. Just check your calculation. I'll give another sum also. But did you get this 0.36711?
0.38.
Mistake in calculation, nothing else. If you get this and multiply with 931, you are going to get the binding energy. And then divide, that value should come as 341.87. And when you divide this value with what? 40, you will get BEN. and BEN will become equal to 8.547. If you are getting anything around 8.5, it is correct. Too big. 54 if you get, be happy. Simple question, right? This question can be given to a student studying in 7th standard also. Don't you think so? Multiply, add, subtract, multiply, divide. ZMP plus A minus Z into Mn into, sorry, minus M nucleus into 931.5 divided by mass number. So, subtraction, addition, multiplication, division. If you are good in these 4 things, then you are going to get the answer correctly. But yes, yeah, because maximum value is itself 8.7 only, that is iron. Okay, I will not break your heart. Take the next question. Yes. At least this solve correctly, please, please, please. Those who don't know what is alpha particle. What is alpha particle? Helium nucleus. 8.547 to be exact. Next question they have given to find the binding energy of which particle? Alpha particle. Alpha is helium. Hydrogen they have given. Okay, why they have given this new? Hydrogen atom means proton. 1H1. 1H1 is what? Protium. No neutron, only proton. Don't confuse in this. So they have given the mass of the proton, they have given mass of the neutron, observed mass of helium, and obviously 931 they have given. So what you will do once again?
There's no neutron, sir.
In hydrogen only, man. What they are asking to find? Alpha particles binding energy, not hydrogen's binding energy. Okay? Alpha particle is what? Isn't it? So mass number is 4, atomic number is 2. So mass of number of protons is 2, number of neutrons is also 2. I told one. Once again, do Z into MP plus A minus Z into Mn minus mass of nucleus into 931, and you will get the value of delta M, and multiply with, divide with, multiply with 931.931, you will get the binding energy, and then divide by 4 here, you will get the binding energy per nucleon. This is a simple question actually, compared to last it is simple. Solve calmly, don't do mistake, please. Calmly you solve, patiently, don't have any hurry. Timer, 3-minute timer this time. Why? Because this is helium here, small nucleus, so small time. Why big numbers? Same numbers only. 3 minutes timer started. Guys, fast. Before the music comes, finish. They said from tomorrow rain, 10 days. Have you heard this? Heard, no? Not heard. In news today I saw. For God's sake, please tell the answer for this year. Zero point binding energy per nucleon. That is too low. Binding energy is itself 0.2. It will be further smaller than binding energy per nucleon. Wrong. What answer are you getting? Tell me the answer. Tell me the binding energy first. 30 point? Near but not correct, huh? Little near to the correct answer. Binding energy is 28.1 as answer key. Yeah, you should not miss, no? BN how much? BN how much? Divide by 4, that's all. Do and tell. Okay, wait, correct. The answer for this question, still 30 seconds are remaining. Try to get everybody, please.
Sir, binding energy 28.29887.
Okay, accepted. 28 point? Ben how much? 0 point how much? 28 point something divided by 4, how much it will be? 7 only, no? 40 by, you are for calcium you are finding, huh? 28.09 they have given. That is 28.097 in this book they have given.
Getting 0.94.
Correct, no problem, huh?
Sir, 28.13.
Sir, I'm getting 8.04.
8 point? Too much high.
7.0.
7.04 is correct, huh? Correct, 28 point something is coming, be happy. If 30 point, 32 point, 44 point, 1 point, then wrong. 28 point something if you are getting, how much you are getting the darshan? Okay, accepted, be happy, what is there in that? But in exam they cut half marks, then I will not be responsible, okay? 28 point something is the binding energy and 7 point something is the binding energy per nucleon. Are you understanding now? Nitya, who has joined online, are you able to understand what we are teaching? Somebody, by some Nitya, somebody was there. Huh. Gun. Who is it gun? What is? Somebody has joined with gun symbol you are saying. Oh, that's why I asked. Mother is joining with gun. Nothing there. Oh, your mother name is Nitya. Is it so? Mother name is Nitya, right? Then maybe your mother only would join. Okay. To see whether you are studying or you are doing something else. Okay, Nitya ma'am, he is there. Who has joined from Nitya name? Can I please know? Please unmute yourself. Yeah. May I know who is this? Nitya, which class you are studying? Class 11? 12, which school you are? Sunshine. Okay, SSM Sunshine, Krompet SSM. Okay, not mother Nitya, man, somebody else. Okay, fine, Nitya. I hope you are understanding what I have told. Are you understanding? If there is any doubt, don't hesitate, you can stop and ask, okay? If you have any doubt, ask me. Not only Nitya, everybody who is there in the online, please ask if you have any doubt. I hope this is clear. The answer for this question is 28.0 something for the binding energy and binding energy per nucleon is 7 point something. Have you got the answer, Srinidhi? At least coming for the online class. 36 is very far from the real answer. Here it is wrong. Check your answer. Okay. Break is over. This was only the break. Okay. So now, what you are asking? Something you are asking? Okay. I hope you have understood what is the meaning of binding energy. Binding energy is the energy which the nucleus is short of to once again become independent. I will repeat, don't write anything, but first listen, I will give time for writing. I said that light, so now see here. So if I had 8 protons in oxygen and 8 neutrons in oxygen, I got a binding energy of how much for oxygen question we not solved. We solved calcium question. Okay. In calcium we had 20 protons and 20 neutrons, and we got the binding energy per nucleon was 8 point something. Isn't it 8.6 something or whatever? 8 point some value came for the energy of calcium. It means that calcium is 8 point something. Actually, bigger value came for the full binding energy of the nucleus. How much it came? For binding energy of nucleus for calcium, how much you got? The previous question, 340 around something. So the calcium nucleus is short of this 340 MeV energy to once again become independent. Are you getting? I'll repeat what I am trying to say. In the previous slide, if I go to the slide, I was saying you that, for example, carbon when it exists in its independent form, it has a higher mass. If it exists in combined form, it has lesser mass. What is the mass defect? When you multiply with 931, we get how much binding energy it has. Since that binding energy is there, why the name is binding energy, you know? Because that energy is not there with carbon, that's why it is not becoming once again independent. If that energy would have been there with carbon, once again it will come in the independent state. I'll repeat, in the independent state, it has this 12 energy. In the combined state, it has energy less than 12, 11.5 let us assume. It means carbon nucleus is 0.5 energy short to become once again independent. If it would have 12 energy, it will once again become independent. But since it is not having that 12 energy, it is binded together with each other. That's why the name is binding energy. Are you understanding? Right, binding energy. Binding energy is the energy, binding energy is the energy which the nucleus is short of, SHORT, OF is off, okay, which the nucleus is short of, to once again become independent, nucleons. In bracket you can write protons and neutrons. To once again become independent nucleons. In bracket you may write neutrons and protons. I'll repeat, Jayaditya. Binding energy is the energy which the nucleus is short of, to become independent nucleons. What you are asking, Rahul? I should once again tell. I'll repeat, you listen. I said that binding energy is the energy which the nucleus is short of, OF off, for once again becoming independent. For once again becoming independent. Written, Rahul? Shall I proceed? Okay. So now you understand that a particular element's BN is giving you an idea how much energy it is short of to become independent. So if a particular nucleus is having 3 BN, it means it is short of 3 MeV of energy to become once again independent. If a nucleus is having 5 BN, it means it is short of that 5 energy to become independent. If a nucleus is having 8 BN, it needs that 8 MeV of energy to once again become independent. Are you understanding? So the higher the binding energy, the more energy it needs to become independent. Are you getting? So which will be more stable nucleus which has higher BEN? Which will be less stable nucleus which has lower BEN? If I compare two nucleus, one nucleus having 1.5 BEN, one nucleus having 7.5 BEN, who will have more stability? 7.5 BN. Why? Because it needs 7.5 MeV of energy to become independent, whereas other nucleus requires only 1.5 B energy to become independent. If I compare alpha particle with calcium, alpha particle is having less BEN, calcium is having more BEN. Who is more stable? Calcium will be more stable because it needs that 8 point something energy to become independent, and this needs only 7 point something MeV energy to become independent. Are you understanding this? Sure? Sure? Okay. If you understand this, then you will understand this graph also, where we have plotted almost all the elements of the periodic table. If you see on the x-axis, you have the mass number. If you see on the y-axis, you have what? You have BEN. And if you see, the BEN varies from where to where? From this value around 1 point something to this value, which is around 8.65, around 8.7 around. So what is the minimum value of binding energy possible? 1 point something. And what is the maximum value of binding energy possible? 8 point something. And which element has the maximum? Iron, ferrous, Fe56. So the element which is the most stable element in nature is what? Iron. Maybe that's the reason it is abundant in the nature. It is the most stable nucleus, remember that. I am not talking about the whole universe, only the earth I am talking about, that existence. So ferrous is the most stable, and which is the least stable. If you see the diagram, you will realize that this deuterium, I think it is. Yes, it is deuterium. Are you seeing this? This deuterium is what? Least stable. And if you see the graph, you will realize that as we move, see, when we move in the x-axis, what we are doing? We are moving in the mass number. It means we are moving from first, second, third, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, aluminum, magnesium, silicon, phosphorus, like that we are moving, isn't it? So when we move in the periodic table, we see that the binding energy is increasing, and then beyond this line, if you see, it is becoming stable, that is having energy more than 8, isn't it? So almost all the elements till this range is having BEN more than 8. Do you agree? So all the mid-sized elements are highly stable. Whatever elements you can think of in this range, they will be highly stable. Why? Because they have a great BEN. But if I once again start going from above 170, that is, this number is almost 170, and this number is almost 30. So all the elements which are lying between 30 and 170 shows a good stability in nature. Elements less than 30, elements more than 170 mass number, their binding energy is less. That is, if you see, the graph starts coming down, and if you see the top series alone, uranium 238, it has very less binding energy, not very less, less compared to these elements. And if you come on the left hand side below 30, then see nitrogen, lithium, helium, tritium, deuterium is having too low binding energy. I hope you are understanding. Light, these elements are called as light nuclei. Why light nuclei? It has less atomic mass number, isn't it? Why I am calling light, you are understanding? Less mass number, so light. These are called as heavy nuclei because they have more mass number, more nucleons. And these are called as mid-sized nucleus. Mid-sized nucleus. So what I am coming to know by this graph? sized nucleus having mass number varying from 30 to 170 shows great stability. Light nuclei which have mass number less than 30 shows less stability, and heavy nuclei having mass number more than 70 also shows less stability. Do you agree with me? Any doubt in this? Very basic thing I have told. Any doubt you ask me? I hope no. If no doubt is there, then the same thing that I have said to you, I have written in this next slide. Oh, I have gone back, where I have mentioned that binding energy is high. In which range? This you can write now. In the range 30 to 170. Light nuclei less than 30, like hydrogen, they combine to form heavy nucleus for greater stability. Okay, they have talked about fusion and fission. We'll talk about that also today. And heavy nuclei, they are also highly unstable, and it breaks into two nearly equal nuclei which are stable. This is called fission. Write these three things you write first. All of you online, offline people, everybody, please copy these 3 points. Important thing. Next discussion is from this only. Darshan, is he coming now? I made your friend Mahesh Raj to attend online. I know you're wrong, so I made him. What Mahesh Raj? Your friend Darshan is sitting here, missing you. Okay, okay. Written? Where you left Adityan? Where you left Adityan? He had some other class today. Oh, math class is there for him. I hope all of you have copied. Fast. What shall I dictate you, Shweta? Last is heavy nuclei. In bracket you can write A more than 170 are highly unstable and breaks into two nearly equal nuclei. Breaks into two nearly equal nuclei which are stable. This process is called nuclear fission. So the next concept is about fission and fusion, and fission and fusion you can understand only if you understand the concept of binding energy release. Shall I go to that topic? There also, both sides is there. Thank you. Okay, so yes, I will once again come to this graph. I'll freeze this. Yes, yeah. Pay attention, guys. The most important part of this chapter has come, where you will understand what is fission, what is fusion, and how it is taking place. Okay. So now you see that these elements which are having binding energy less than 875 are less stable, right? If they want to become more stable, they have to increase their binding energy. Even this uranium, if it wants to become more stable, it wants to increase its binding energy. Are you getting my point? This big nucleus, if it breaks into two small nucleus, not small, mid-sized nucleus, suppose it is having 238, below it will be 92 around. If it has 92 atomic number and 238 mass number, if it breaks into two nucleus which are having mass number around 112 and 112 or 115 and 115 around, then it will come in this range. This is having 238 mass number. If it breaks into two nucleus which has mass number, how much it will have? 238 means it will have 120, 118, right? Or it will have 110, 128. All these nucleuses are coming under the category of mid-sized nucleus, and mid-sized nucleus are highly stable. They will attain stability. Okay. So, if my uranium breaks into two parts, these two parts are what? Two mid-sized nucleus. It can be barium, strontium, many things are there. We will talk about that also, those elements. If it breaks into two mid-sized nucleus, then it is going to become stable. That you understand first? Okay. Same way, if this deuterium or tritium is somehow converting itself to become helium, it will become more stable, because these are having low binding energy. If it somehow becomes helium, it will have more binding energy, it will become more stable. Are you understanding this first? That uranium to become stable, it has to break into two mid-sized nucleus. Hydrogen has to become stable, it has to become helium or something in this range, because it will increase its binding energy. Surprisingly and interestingly, we found that when any nucleus of low BE is getting converted into high BEN, it releases energy. Now, this is very difficult to accept our brain. How something is combining, it will release energy, it will need energy to combine, no? Or how something is breaking, you want to give energy to break it, no? If I say you give energy, it breaks, I can understand, sir. But you are saying it is breaking energy, is releasing, it is difficult to understand. Or if it is combining to release energy, it is difficult to understand. If I say that there is one stone and you are hitting by a hammer, stone becomes 2, you may say, sir, here you are giving energy to break the stone, right? But what I say, if uranium is breaking into two mid-sized nucleus, it is releasing energy. Now, what happens? I will explain. Be concentrated. Don't see light, camera, TV, and all these things. Be concentrated. Uranium is having binding energy of around 7 point something, 7.65, I think, approximately. If it wants to convert into barium and strontium, which are having binding energy around 8.5, 7.6, 8.5, don't you think it has to release that itself, that 0.9 MeV to become 8.65? Now, you may say, sir, in 7.6 only if we add 0.9 we get 8.5, no? Why are you selling release? Binding off. Binding energy is the energy which the nucleus is short of to become independent. I gave the definition before some time. Uranium is how much energy short of? 7. If it wants to become 8 energy short of, it should release 1. Understanding something? Not? I will repeat. Uranium binding energy per nucleon is 7.65. It means if 7.65 per nucleon is given to it, it will become independent. If it wants to convert into barium and strontium, which are binding energy 8.65 or 8.5, whatever, then it has to release 0.9 MeV more from it now to become 8.6 binding energy, because that 8.65 binding energy, 8.5 binding energy means it has to get 8.5 to be independent, and something is having 7.6, it means it needs 7.6 to become independent. If it wants to become something which needs more energy to become independent, it has to reduce its energy, no, not increase its energy. Are you getting? Already it was short of how much? 7.6. If it wants to become 8.6 short of, it should release one from itself. That is why energy is getting released. I will repeat this for fusion now. Now, if you are having deuterium or tritium, which is having a low binding energy around 1.5, if you want to make it into helium, which is having around 7 point something, so 1.5 BEN, it means it needs only 1.5 to become independent. Somehow I make into helium, which is having 7 BEN, then it should release from itself 5.5 BEN. Then only it can come to that stage of releasing 7 BEN to become independent. A more stronger nuclei needs more energy to become stable, right? If a low BEN nucleus is getting converted into high BEN nucleus, that is only possible if it releases more energy from itself. Then only it can become that element which needs. Anybody has doubt, you can ask me. Yes, ma'am. Jai Aditya. Okay, just pay attention first. Okay, I'll once again repeat, pay attention. I'm repeating. So I said that a particular element is there. Okay, Jai Aditya, a particular element is having 5 B. Assume. Okay, you let it be unmute for some time. Aditya, you can be unmute for some time. Yes. So a particular element is having 5. Aditya, it has to become an element which has 7 BEN. What it should do? An element which has a BEN of 5. It wants to become an element which has BEN of 7. What it should do, Aditya?
Energy to become
How much it should release?
2.
2. Why it has to release 2? Because if it is releasing 2, then it will become 7 short of to become independent. Am I right, Aditya?
Yes, sir.
That is what is called as binding energy release. For low BEN to become high BEN, it is releasing outside. That what it is releasing outside is only called as binding energy release. Still half an hour is there.
It's already short.
Huh? Tell me again, man, Aditya.
So it's already short of 5.
Yeah,
Then when we release 4, it becomes short of 7.
obviously.
Which is what?
That's what I'm trying to say. So if it is releasing 2 from it, it is becoming 7 short of now. That 2 got released, no? That only we are using for our purpose. And remember, we are talking about binding energy per nucleon. One atom has 238 nucleons. Each nucleon is creating 0.9 MeV. One atom of uranium itself is having 238 nucleon. If you want to find how much energy is released by one atom of uranium, it will be 238 multiplied by 0.9, around 200. So 200 mega electron volt will release by one atom of uranium. And in one element, how much atoms you have? Avogadro number, millions of atoms. All atom will produce how much energy? That millions of atoms multiplied by 200 MeV. That much energy is released outside. That's why fission reaction is producing a huge amount of energy. Are you getting my point? When we see fission, like atom bomb, who dropped? Japan dropped. On Japan it was dropped. Pavam Japan. Who dropped? USA dropped, right? Little boy and fat man. Fat boy, fat man, I think. Fat man, no, and little boy. Whatever, or little man or fat boy, I don't know, whatever. Something. So, yeah, it took and dropped something. Whatever something was. This bomb only, no? Atom bomb, we say. One thing is hydrogen bomb. Hydrogen, if they drop, that's all. 5 hydrogen bomb on Earth is because about that. But atom bomb is fission. Fission is the process which releases a tremendous amount of energy. What they do, you know, they will take on uranium matter, they will bombard by using neutron. Neutron goes and hits uranium, Uranium was unstable because of two reasons. One was having low BEN, second was having if the distance becomes more, less. So uranium kind of nucleus is having bigger, so it has less, so it is already unstable nucleus. Are you getting my point? And additionally it has low BEN also. Neutron nuclear force will further decrease, it will disintegrate into two size and releasing 0.9 MeV energy per nucleon and also releasing 3 neutrons. These 3 neutrons will once again go and hit some other uranium and this chain reaction keeps on happening and then we get huge energy, and that energy can destruct a lot, like what happened in Hiroshima and Nagasaki. Are you getting? We'll come to that point now. So I hope this concept of binding energy is a bit clear. Still you can ask me. Online people, Praneep, Rahul, Salvin, Srinidhi, Tanishka, Uttara, Vignesh, Amruta, Jayaditya, Navadipika, Nitya, understanding whatever I have told? Say yes, yourself, at least I will be listening, understanding. Thank you, thank you. So now let us talk a bit about what? No, this I'll talk last. First I'll talk about, yes, fission and fusion. Just now I said, what is the meaning of fission? Write down where. When heavy nucleus decays into two or more intermediate mass fragments, it is called as fission. Write this out. What is fission definition? Fission is defined as when heavy nucleus decays into two or more intermediate nucleus, isn't it? And what is fusion? When light nuclei fuses into a heavy nucleus, actually not heavy, heavier, because it is not heavy, it is heavier than the light nuclei, that's all. That is called as fusion. Fusing into a heavy nucleus. Heavier, not heavy, heavier, heavier than that light. That is fusion. Have you written it? Make it fast. We have only less than half an hour remaining. It's a 2-hour class. You have to carry water bottle. No food allowed inside the studio. Okay. So whenever you come for this class offline, they have the liberty sitting. No, all the snacks packet, Pepsi, Cokes, everything will be there near them. They will eat and drink whatever they want. But you don't have. So carry your water bottles when you are coming here, and don't carry any food items when you are coming inside. Shall I proceed? Salvin, Mario, shall I proceed? Say yes by unmuting yourself. Okay, thank you. I am proceeding further. So as I said, what is fission? Splitting. So what happens, the diagram I have drawn to make you understand. Neutron is going and hitting a target nucleus, and you are getting the byproducts, and neutrons are coming out. I said, see, it's not like always 3 neutrons will come out. There are 3 possibilities. See this diagram, you will realize. In fission, there are 3 this diagram I have taken from NCERT book only. There are 3 possibilities. One possibility, see, pay attention. One possibility is, if a neutron is going to hit the uranium, then it can break into barium, krypton, releasing 3 neutrons, or it can break into antimony, niobium, releasing 4 neutrons, or it can break into xenon, strontium, liberating 2 neutrons. When this particular reactions are taking place, that time not only energy gets released, in all the cases plus some energy will also be there, plus binding energy also will be there, plus binding energy will also be there, isn't it? Apart from that, this 3 neutron, this 4 neutron, this 2 neutron is coming, no, they are enough for further continuing reaction. Don't think if I am having 1 million uranium nucleus, I need 1 million neutrons. 1 neutron is enough. 1 neutron will start the reaction. See all the 3 possibilities, what we are getting? 3 neutrons, 4 neutrons, 2 neutrons. They will carry forward the reactions, isn't it? This 2 will go and hit once again uranium, some other uranium. This 3, 4 will go, 3 will go. In each case, there will be some binding energy release. Why releasing? I said you.
Number of neutrons released.
Loudly, loudly.
What determines the number of neutrons released?
What
It's 2, 3, or
what is getting formed that determines how much neutrons released. See here, barium and krypton is forming, right? So what is the atomic number? 56 plus 36, that is 92. What is the mass number? 89 plus 144. If you add, you will get 233. Check. Then 3 are remaining, so you will have 3 neutrons coming out. If you see niobium and antimony, 51 and 41, it will become 92 only. But add the mass number, 99 plus 133, you will be getting 232. Check. So how much remaining? 4 remaining. So you are having 4 neutrons releasing. Are you getting, Mr. Jayaditya?
yes, sir.
What is getting formed by breaking, that decides how many neutrons will come out, whether it will be 4, 3 or 2. Any problem, Sangvi? How many number of neutrons will come out is purely depending upon what is getting formed after the breaking of uranium. In board examination, you must remember these reactions and go, because they will ask, write short notes on nuclear fission. That time, if you don't write reaction, they'll cut marks. In the board examination, you are supposed to remember these reactions for the examination. Same way, if we are having fusion, that is, 2 light nuclei is combining to become a heavier nuclei. Once again, same thing is happening. A low BN is becoming high BN, and if BN becomes high BN, it is possible only if energy is released, and that is the process called as fusion. But you know, if I ask you, out of fusion and fission, which will produce more energy, what will be your answer? Why? Why fusion? Why not fission? Answer lies here only. Where? In the BN diagram. So if you see BN diagram, you yes, less binding energy release here. If you see this diagram, when a big is breaking into 2, then the amount of BN coming is only 0.9, because 7.6 to 8.5, only 0.9 releasing. But when 1.5 is becoming 7 point something, 5.5 MeV is getting released. So obviously, nuclear fusion reaction is having much more energy compared to fission reaction. That is happening in where? Hydrogen bomb, obviously, and where naturally? Sun. What is happening inside the sun? Fusion reaction is taking place. Hydrogen is combining to become helium. Hydrogen, helium, hydrogen, helium. That only is happening. And that's why one day it will get over. Reaction is there, no? It will get over one day. It will take millions of years. Then sun will be dying off.
Sir,
Please tell me.
each nucleon in uranium has about 7.6 MeV, right, sir?
Yes.
Then we have like 238 nucleons.
Yes, there you have less nucleons.
Yes, it's compensated much greater than 238.
Exactly. But
So much energy is
I'll tell you.
in one atom of uranium.
Helium abundancy and hydrogen abundancy. Do you know what difference is there? Huge difference is there. Am I right? So hydrogen can be acquired from the nature itself. Reaction taking place, right? Hydrogen molecules. From there itself will take energy. But for uranium, you will not get uranium anywhere, no? Uranium has to be taken out from the earth, and it is having obviously much. It is like millions of times lesser than the hydrogen availability. So, even hydrogen can be acquired from the atmosphere and reaction is happening.
But if you consider uranium and 2
Um,
atoms of hydrogen,
Then obviously this is only having more. In which case, if you have only 1 atom of uranium and 1 atom of hydrogen consideration, yes, you are true, more energy. But in nature, it doesn't happen like that. In reality, hydrogen can be acquired from atmosphere itself. Too much of hydrogen is there compared to uranium. For uranium, we need specific uranium atom only, isn't it? For hydrogen, have 1 atom, rest it will take from the environment. But problems are there. I'll come to those problems. Can I proceed further?
spontaneous, right?
That
To
is
supply energy to the
exactly. Why it needs energy?
temperature, pressure.
Why? We'll come to that point. Coming. So we are talking about fission, and now We'll talk about fusion, a bit fusion we'll talk. So yes, these things you understood, I hope. If you want to write this, you can write from NCERT book. NCERT book, this has these 3 reactions. I have taken this photo from NCERT only, you can write from NCERT later. But yes, this I want to speak a bit about this, which you know already, that there can be many different possible reaction products, isn't it? I told 3 possibilities. Reaction produces more free neutrons than it uses, obviously. Using 1 neutron, producing either 2 or 3 or 4 neutrons. So always the product neutrons are more than the reactant neutrons. Then these free neutrons can then induce fission in other nearby uranium nuclei, obviously. So we don't need much neutrons, 1 neutron is enough, and this reaction releases energy. Extra binding energy released in form of gamma rays and through the kinetic energy of the particles produced. That is energy being released from the nucleus. I'll come to the main point. Yes, this is what the calculation is. So binding energy per nucleon of uranium is how much? 7.6, I told you. And what is the product's binding energy? 8.5 MeV approximately. So how much energy is released? 0.9. If there are 235 nucleons, how much energy is released totally? Multiplied by 0.9, 210 MeVs. So for 1 gram of pure uranium, this would correspond to a total of about 9 into 10 to the power 10 joules of energy. Can you imagine how much is that? 1 gram of uranium is equal to 2 tons of coal. 2000 kg of coal you want to produce the energy. What can you produce by only 1 gram of uranium? That's why we prefer nuclear power plants over thermal power plants. I started last day, I started this only. It may have a lot of problems, but it can help you by saving 2000 tons of coal. 1 gram of uranium. If you have 1 kg of uranium, imagine how much energy you can produce. Are you getting my point? So 1 gram of TNT releases about 4, imagine TNT, which is like a bomb that you use for detonating. That itself is releasing only how much? 4200 joule. It is called as bomb. What is this? 10 to the power 10 joule of energy. That's why it is called as atomic bomb, isn't it? Fine. Next I have written the reaction of what? Fusion. As I said, fusion also have many possibilities, like protium combining to become what? Deuterium. Deuterium combining to become helium, or deuterium may become tritium and protium also. In all these reactions you see I have mentioned here 0.42, 3.270 or 4.03 energy released, and I have forgot to mention one reaction that is there in sun, not mentioned here. In book it is given. So if you see that reaction, you will realize that even the sun, what reaction is taking place inside. The concept is same, that there also the fusion of hydrogen is taking place. Now I will come to the main point. One second. Time is little there. I will come to the main point. So we can see very clearly from the binding energy curve that fusion is more better than fission, isn't it? One more advantage of fusion is, in the case of fission, we have byproducts coming out, isn't it? Like barium, niobium, strontium, xenon. All these elements are also having radioactivity, are actually bad for the environment. What you are doing in the ocean. If you see kalpakam, while doing the atomic reactions, they are producing lot of byproducts, and those byproducts are not safe. So we are disposing in the ocean. But if you are able to make nuclear fusion reactors, no? What is byproduct? Hydrogen, helium, all are clean energy. That's why nuclear fusion reactors are called as clean energy reactors. Not like fission, where we are going to get byproducts. In the case of fission, what you are going to get? Barium, strontium, all these things, which are again a problem for us to dispose. In the case of fusion reactors, nothing, no tension. What you need is what? You just need hydrogen to combine. Now the problem is, okay sir, this much is there, then why are we doing fission reaction? We can do fusion reaction itself. That much you are telling it is good, advantageous, everything you are telling positive about fusion, then why are we having fusion itself? Make it fission alone.
We are not
problem in fusion is you are going to combine two hydrogen, right? Hydrogen, when they are coming very close, very close, very close, we will experience a very, very, very strong proton-proton repulsion barrier. One proton, another proton, they will repel each other. And the more close it comes, it will have more force of repulsion. F is equal to k q1 q2 by r square. R becomes very, very, very small. F becomes very, very, very large. So it is highly difficult to fuse two hydrogens. Though theoretically we are saying, in reality it is very difficult. You know what we do for that? We have to conduct a fission reaction to generate that much energy. Energy required is almost 10 to the power 7 kelvins of energy. If I see NCERT book, they would have given it. The energy required to conduct is almost 3 into 10 to the power 9 Kelvin. If you see the NCERT book, it is written, page number 316, they have written that energy required to overcome proton-proton repulsion barrier needs temperature of 3 into 10 to the power 9 Kelvin. How do you produce that? Not easy, right? You cannot burn stuff and produce that, or you cannot burn paper or wood or something or anything. Even electricity cannot produce so easily. Usually they will do by using, in China they are doing that, but it is highly difficult to produce this temperature. So what they do, many countries claim that they have hydrogen bomb, right? Israel tells we have hydrogen bomb. China says we have hydrogen bomb. Russia says we have hydrogen bomb. They have truly also. Then what they will do in hydrogen bomb? One chamber for fission reaction. One chamber, hydrogen, that's all. Drop it. When it drops, fission will take place. Huge energy will be produced. Have you seen how the blast happens? That much heat is produced. By everything gets evaporated, not even burns. Wherever the bomb is dropped, no. Nearby, like half a kilometer radius, everything gets evaporated. That much high heat is produced. That heat will be used to fuse the hydrogen, and then disaster will take place, because that will be tremendous chain reaction, isn't it? Hydrogen is everywhere present. It will, all the hydrogen will start combining, and what energy will be released, like sun, and that's why it will become uncontrollable. Every country is restricting itself to use hydrogen. That is the problem, and that is the problem. Why are we not having nuclear fusion reactors still in the country? Country what? World? We don't have. We know it is safe. We know it is clean, but we know if little bit here and there happens, no, gone. Country itself will be erased from the map. That much powerful is fusion reaction. But China claims that they have some fusion reactors where they have produced energy like sun. They say controlled manner. What China says, we cannot trust that, but they say. Okay. So fusion reaction, I hope you understood what is the meaning of fusion reaction and why fusion reaction is difficult. Fusion reaction is difficult because proton repulsion barrier, and to overcome proton repulsion barrier, we need almost 10 to the power 9 Kelvin of temperature, and to attain that temperature, once again we need fission reaction only. Okay. Next thing is, 10 minutes are remaining, I will take 10 minutes. Next thing is, why are we preferring fission reaction? One more reason is there. That reason only I am going to talk, last topic of this chapter. What is that one reason? One reason is nuclear force. I talked about this in the last class also, once again I am repeating it. I said that inside the atom there are, you want to sing, I mean, he's going to end, what man? Tell faster. Who is that? Man, oh, Satish sir is there. I thought some student is told like that. Coming back. So please pay attention. So I was talking about Coulomb's force and nuclear force. I told you in the previous class itself that inside the atom there are multiple forces, but we are talking about two forces now. One is Coulomb's force of attraction and repulsion. You know that if there are like charges, they will repel each other. If there are unlike charges, they will attract each other. At the same time, if you are having a nucleus, inside nucleus you have what? Nucleus is filled of protons and neutrons. Slept already. Nucleus is filled of protons and neutrons. Neutrons are neutrally charged, neutral, and protons are positively charged. Since the protons are positively charged, it is trying to repel each other. But why it is not able to break the nucleus is because of nuclear force, which is a strong, attractive, short range force. I told this in the previous class. It is attractive force, and this force of attraction acts between all nucleons: proton, proton, neutron, proton, neutron, neutron. So every neutron, neutron will also have attraction. Proton, neutron, attraction. Proton, proton also attraction by nuclear force. But the problem with this force is, it is a very short range force. If the two nucleons are very close only, it will act. If it goes far, it will not act. That is very good depicted by this graph. You see this graph, you will realize, sorry, this graph is saying, see this graph. You will realize that as the distance between the two, see here potential energy is there, positive, negative. So at this point, negative potential energy means strong force of attraction. I hope you know this. Negative potential energy means strong force of attraction. Positive potential energy means that is repulsion. Those who don't know from 11th standard, if potential energy is negative, it is attractive. K Q1 Q2 by R is potential energy. Am I right? If Q1 Q2 are unlike charges, then only it will have attraction, and that is possible only if it is negative.
Yes, sir.
If both are negative, negative, it will become positive. Both are positive, positive, it will become positive. Only if it is one is negative, one is positive, it will remain negative. So it means that this shows repulsion. This shows attraction. Am I right? So you can see very clearly from here that as distance is reduced between the nucleons, the nuclear force is maximum. And as you go away, that is distance between them is too much increasing, then the nuclear force almost becomes zero. One more thing is surprising, you see here. Too much coming close also is not good. If it becomes too much close, at one point nuclear force becomes zero also. And if it comes more closer, then nuclear force becomes repulsive in nature. I said nuclear force is attractive, no? One question is there. Is the nuclear force always attractive? I will say no. Nuclear force may become repulsive if the distance between the two nucleons is less than 1.8 Fermi. This distance is actually, inside they have given anything, around 1.8 Fermi. So if the distance between the nucleon become less than 1.8 Fermi, what will happen, you know? They will start to repel each other. That is quantum mechanics, if you want some other day. So now you understand that if two nucleons are in this range only, they are going to experience the best attractive force. And almost all the elements, almost all the atoms, almost, not everything, are having nuclear force in this region. So it is having a strong force of attraction. Now imagine uranium. Uranium is a big nucleus. If it is a big nucleus, then its nuclear force of attraction will be less because it is coming in this range somewhere. And if it is less, then what is going to happen? It is going to be unstable because of having less nuclear force and more electrostatic force of repulsion. And that is what happens in fission. And that's why fission is more preferable, because already you are having a weak nucleus, 235 nucleus is there, nucleons are there, no, they are a little bit unstable. Add one more nucleon, neutron is adding, it become very much highly unstable and it will break down. Are you getting another reason for preferring fission? Because uranium nucleus is already unstable due to low nuclear force compared to Coulomb's force. So the moment a neutron is hitting the nucleus, it is further reducing the distance between the nucleons. 235 itself, it was unstable, I added one more. What will happen? Highly unstable. And what will happen? It will break. So that is the reason why fission reaction is preferred over fusion reaction. It is easy to take place. I hope you are understanding. Amruta, understanding or not?
Yes, sir.
Yes. I hope everybody who is there in the online, they're understanding whatever I have said. I have almost come to the end of this topic, today's discussion. And before I wind off, I want to ask a few questions. So people who are sitting on offline, be silent. I'll give chance to answer, then you answer. Don't shout anything. Okay. So this question is, online people don't drop because I'm going to ask question. Be in the class itself. Okay. So the first question is for Salvin Mario. Salvin, unmute yourself, please. Simple question is coming, man. Answer fast. The question is, which of the following is not correct about nuclear forces? The four options are: they are short range attractive force, they are independent of charge, they change to repulsion at very close distance, they obey inverse square law. A, B, C or D? Fast. Loudly, loudly. What do you think C is saying? C for cat or D for dog? Okay, see, he says C. Navadipika, what do you think? Whether what Salvin is saying is correct? Is it C? Navadipika?
Yes, sir.
Okay, she also agrees. Very good. Nitya, what is your opinion? Nitya, loudly, I am not able to hear you. What is your opinion? Did she say C? Okay, you be silent. Only I can hear them here. Okay, fine. Srinidhi, what is your opinion? Srinidhi, loudly. My God, sitting here. Obviously D, yaar. Just before some time, so you are sleeping. I said that. I said that if it becomes very close, it becomes repulsive in nature. I said no. By showing that graph, I said if the nucleons are very close, they will be repulsive in nature. So what is the option which is not true about nuclear forces? Option D. Okay, no issues. Next question is to Rahul with camera off. Rahul with camera off. Today we allowed you, man. Not next class. You see next class. Rahul with camera off. At least say yes or no, man. Dropped. Very good. Okay. Vignesh, are you there? No, he is there still, Rahul. Not on in the mic. Vignesh? Yes. Next question is for you. Bala sir, can you increase the volume of the TV? Yes. The question is for you, Vignesh. Maximum make it. Nuclear force between two protons and a proton and a neutron and between two neutrons are FPP, FNP and FNN. Which is true? Vignesh, I am expecting from you. Give a try.
Option yes.
Option A. Okay. Uttara, what do you think?
One second, sir.
I hope you are not browsing.
No, sir. I'm just thinking.
Yeah, please think. No problem. Still thinking, Uttara?
Yes, sir. I am confused right now.
Okay, give a inky pinky ponky and try one answer.
Is it okay? I think it's D. No, it can't be D. No.
Okay, give a try, whatever. No problem. Choose something.
Okay, I'll go with D.
D. Okay. Then I'll give a chance to Srinidhi. Try your luck. Try. Something. Unmute yourself first, Srinidhi. Yes. Something? I'm not able to hear anything. Or not saying itself.
Sir, I think B.
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 Okay. Nitya, what is your opinion?
It's option C.
Option C. I hope you have not browsed. Yes, option is C. Option C is correct. That is FPP is equal to FNP is equal to FNN. Obviously, all the forces are same. I said nuclear force is independent of charge, whether it is neutron, neutron, proton, neutron, proton, proton will have same force. I hope you are understanding, Uttara, why.
Yes, sir.
Okay. Next question. Next question is for Mahesh Raj, Darshan's friend. Mahesh Raj, listening?
Yes, sir.
Yes, man. Then tell the answer. Density of nucleus is dependent on mass number, independent on mass number, independent of atomic mass number, dependent on atomic mass number.
Sir,
Huh. I talked in the beginning today about density of the nucleus.
yes, sir.
I told stressfully it is independent of something.
It's mass number, sir.
Which one, man? Dependent or independent? A or B?
Independent. Independent.
Independent of mass number. Very good, man. You should clap, man, for Mahesh has said. What, good. Okay, good. Next question is for Mr. J. Aditya. Huh? Kapil will you want? Kapil will, Sanjit is saying to ask you. I'll ask you. Okay. So, Kapil will is there or he left? He left by now, man. Why he will be there? Same question came. Why it decreased? Oh, question is done. Thank you. Okay, fine, guys. So I hope whatever I have tried to teach you have understood. If yes, then I was successful. If no, nothing can be done. I will teach in the next class to you once again if you want me to. But take care. Bye bye. This chapter is almost done. Now, yes, this chapter is that much only is there. You can go home and see the content. Again, I am repeating one thing. Online, offline, guys, everybody, please read book for this chapter at least. Nuclei chapter, atom chapter, dual nature chapter, that is modern physics chapters. You must read book. Without reading book, don't think of understanding this chapter properly. Also solve the NCERT book back questions. Okay? Bye bye. Take care. Online guys, good night. You can drop off. I am signing out.